Welcome to another video lecture in Math 442. Now I'm going to go back to my slides for section 7.4. So you can also download those on D2L. So follow along or pull them up as you choose. All right, here we go. Section 7.4.3. Now that we're working with a linear system of equations, think about your vector U as a vector of unknown functions. It's got m components, and f is a vector valued function with m components, and I write it in this very simple form, u prime equals f of u. For now, we're just thinking autonomous, so t is not explicitly over there. Now think about having an equilibrium solution to that system of equations. So let's call that equilibrium u bar. It is a particular solution for that system. And now let's think about how we linearize. So U bar is a fixed, usually an equilibrium solution. And then we define a new variable, V of t, and that would be U of t minus U bar, where now U of t is what we really like to think of as a nearby solution to the equilibrium solution. Now, if we linearize that system, it looks like what you see here, and I'll show you how you get that in a minute. And that f prime of u bar, it's a very little subtle notation, but it means a big old Jacobian matrix, as you see here. So f is a vector valued function with m components, and I have m variables, u1 through um. And this Jacobian matrix is the matrix of all partial derivatives of all the f's with respect to the u's. And you're just going to have to take a look at that yourself with a particular problem. What I would like to say about what you saw earlier in the previous video is, remember how we were thinking about absolute stability for Euler's method. If we are thinking about a linearized system, then we say that 1 plus k lambda p in absolute value or complex modulus has to be less than or equal to 1 for all integers p where lambda p is an eigenvalue of. What is our matrix now? Well, now our matrix A becomes that Jacobian matrix right there. So think about this for just a little bit. You're going to look at a Jacobian matrix, and then that Jacobian matrix will have some variables floating around. And what you want to do is plug in that equilibrium solution for all of those variables. So in the end, you should actually get a matrix with a bunch of numbers in it. And now, for Euler's method, what do? I compute all the eigenvalues of that Jacobian matrix, lambda 1 through lambda m. And then in order to guarantee absolute stability, I impose this condition right here. And like I mentioned earlier in the previous video, if I know that I've got a region of absolute stability, then I choose my time step k, so that k lambda p lies in the region of absolute stability for all eigenvalues lambda p. As a summary of section 7.5, I just want to say a few words about this time step k and how it's really chosen. We know that our local truncation error is acceptably small if, our k is less than or equal to some acceptable value in terms of the O of k or the O of k squared. And we've addressed this a little bit in some of the zero stability stuff. I think you've seen that a little bit on your midterm as well. And the numerical method is absolutely stable on a particular problem. There's a constraint, k is less than or equal to some value related to the stability. And now what you would like to see is that you have a constraint for your stability that says you have to take k to be a certain small value. And then you have a constraint for accuracy and a constraint for stability. What's optimal is if those two are of roughly the same magnitude. So if you look there in bullet number 3, if the stability constraint is much, much smaller than the accuracy constraint, then that particular method is not really optimal. Those are called stiff problems, and we explore those in chapter 8. I'd also like to point out that your ODE solver software that you use, at least with MATLAB, it uses embedded methods or predictor corrector methods. So these time steps are dynamically controlled, and I mentioned that before in class. And error estimations are done, and those error estimations are usually around the accuracy, but there are also some estimations done to detect some sort of instabilities. Now, I don't think the details of those stability regions are for those particular methods are really done by the software. It's usually just a method of trying to keep the time step within a certain range. So what I will say at the end here is that the concepts that we've presented in chapter 7 are actually very important, whether one is using an ODE solver or you're even working with time-dependent PDEs. All right, there you go. These are some more details out of chapter 7. Go read through the rest of the textbook and just get an idea of how that works. And we will move to chapter 8 in the next set of videos. Thank you. Thanks for watching. Bye-bye.